Right, okay, in this clip we're going to talk about further additional reactions of alkenes. Page references are 130 and 133 in the OCR AS level chemistry textbook. Okay, so in the last clip we talked about, addition reactions of alkenes. We're going to talk about that a little bit more in detail, and we're going to use something called curly arrows. Now, we talked a little bit about curly arrows in possibly the first clip when we talked about fission, but I'll reintroduce that, and we're going to be able to show the mechanism for these reactions, for the electrophilic addition of alkenes. Now, mechanisms really are just a sequence of steps, and these mechanisms, whenever you draw mechanisms in organic chemistry, they are fantastic, literally fantastic mark gatherers, right? So we need to be able to make sure that we can do these, and we can do these correctly, and you'll realize they're not quite hard. Practice, practice, practice makes perfect, and you will need to use curly arrows for this. So without further ado, let's get cracking. So just quick reintroduction into curly arrows. Now, curly arrows in chemistry, specifically organic chemistry, right, it does have a definition that you need to know, and curly arrows represent the movement of an electron pair. So curly arrows, right, they simply represent the movement of electrons. So let's talk about fission, which is what we've done before, right? Let's say we've got A, B. This is a covalent bond between A and B. If we break the covalent bond and move both electrons towards B, what we're going to do is we're going to form ions, okay? And you'll remember this is the heterolytic fission of covalent bonds, okay? So we've got A and B, and essentially we formed ions, right? But because the covalent bond has broken, B has a lone pair of electrons, right? So we've got B, lone pair of electrons, got a negative charge. Done. That's all you need to know in terms of curly arrows for AS. I'm not going to talk about homolytic fission, right? That's not really important at the moment. We're going to talk about electrophilic addition. And when we have full curly arrows, all they represent is the movement of a pair of electrons to either form or break a covalent bond. The definition for this is in your textbooks, 131 I think, and again, it's just the movement of a pair of electrons to either make or break a covalent bond. Done. Right, okay, so let's put this into context, shall we? We were talking about, in the last clip, we were talking about simple addition reactions, but we had hydrogen and halogen molecules only. Now let's move that into something slightly different. Let's talk about, excuse me, hydrogen halides. Let's start off with hydrogen bromide. So in this case, we've got ethene and we've got HBr. So what is going to happen? We've got an unsaturated molecule. We're going to only make one product. Remember, the pi bond for the carbon-carbon double bond breaks, and we're going to be left over with, well, something like this, HBr. Now, you might be wondering, okay, where will the hydrogen attach? Where will the bromine attach? In this particular case, it doesn't matter because, it's a symmetrical molecule, right? It doesn't matter at all where the hydrogen is bonded to and where the bromine is bonded to. So this was essentially, these are the two new additions that we've got. So it doesn't matter at all which of these two products we form, because in this case, ethene being symmetrical, it doesn't matter, they're both the same molecules, right? It's that simple. So hydrogen halides can attach across the double bond to make a halo alkane. That's all you need to know. The conditions, we don't need anything specific, it's just room temperature. Done. Right, now, what we can also do is another reaction. And don't get this confused with hydrogenation. It's got a very similar name, hydration, but it's where we add steam. Now, one of the key bits that I find students make mistakes is they forget this, the state symbol, right? It's not liquid, it's not gas, it's not liquid, it's not solid, it's gas. So we need to be able to make sure that we recognize and we represent the H2O as a gas. So it's got a state symbol of G. So if we were to add H2O, right, across a double bond, essentially all we're going to have is something like, let's just change the color. Right, we're going to have a hydrogen and an OH. Again, it doesn't matter where the OH goes, where the hydrogen goes. If the OH and the hydrogen were to swap positions, it would make no difference because, again, it's symmetrical, okay? It's symmetrical. So what we formed here is ethanol. So the addition of steam to alkenes produces alcohols. Now, for this reaction, for the hydration reactions, there are conditions which we need to be aware of for this reaction to take place. Specifically, we need a high temperature and pressure, right? But most importantly, we need an acid catalyst, and the acid catalyst which is used is phosphoric acid. So we're just going to, now you'll remember that phosphate is PO4 3-, so we need 3 hydrogen ions to make it complete and balanced, so H3PO4. So that is the acid catalyst. We're starting with something that's unsaturated, we're finishing off with something that's saturated, right? That's all there is to it. Done. We've made an alcohol. This is known as hydration. Let's now move on to a slightly trickier situation where we've got unsymmetrical alkenes. Now what I've got here is propane, right? Remember, we don't need to know about the name, we don't need to number where the double bond is, it's just propane. So we've got propene and we've got HBr. Propene and HBr. Now, it's very similar to the first situation. Actually, it's pretty much the same at AS level. All we have to do is we end up with something which looks like, so what I'm drawing right now is pretty much the same as what we've done in the first step. Let's just change the color and let's move it on. So we've got the CH2, we're going to have a bond there, we're going to have a bond there. Where does the hydrogen go? Where does the bromine go? Well, let's do this. In this case, if the hydrogen and the bromine were to switch positions, right, it would make a difference to the molecule, right? It would. So we could have two cases. We could have either the one that's drawn on top, or we could have this situation here where we've got, let's choose blue, we've got the bromine and we've got the hydrogen there. Okay, now, the reason it's important here is because we've got an unsymmetrical alkene, okay? It's unsymmetrical, so it's important where the hydrogen and where the bromine attach, okay? It is important. Now, because we can form two products, right, we form a mixture. Okay, if we were to do this reaction in the lab, we would form a mixture of these two products. One product is produced in a greater quantity than the other, and so is therefore known as the major product, right? And the second one will be the minor product. In this particular case, the top one is the major, the bottom one is the minor. Now you do not need to know which one the major product is. You do not need to know which one the minor product is. You will not, in an exam situation, be asked, state the major product produced from the addition of a hydrogen halide to this unsymmetrical alkene. You will not be asked. You will be expected to, however, draw both products. And that's easy. All we're doing is we're switching the position of the hydrogen and the bromine in each case. Done. If you're interested in working out in deciding what is a major product, what is a minor product, it was discovered by this chap called Vladimir, this Russian scientist, Vladimir Markovnikov. You know, if you're interested, you know, Kovnikov, I'm certain that's how you spell it. Have a look at that. If you see me, let me know, ask me if you're unsure about that, but you do not need to know for AS level chemistry. Okay, now this is where it gets a little bit fiddly, shall we say. What we're going to do is we're going to use curly arrows to show what actually happens to the bonds, and we're going to show this as a mechanism, so a sequence of steps. Now, as I mentioned earlier, mechanisms, great mark gatherers, because you're going to be expected to use curly arrows. Now, it's really important when we're using curly arrows to clearly show where we're starting the curly arrow and where we're ending the curly arrow, and I'll talk a little bit more about that when I actually start to draw. But let's have a look at the title. Electrophilic addition of hydrogen halides. So far we've only used addition of hydrogen halides, of hydrogen, of steam, but you'll notice we're now starting to use the word electrophilic. Now, electrophilic is based on the word electrophile, which we've covered earlier, and you'll remember that an electrophile is simply an electron pair acceptor. So it's something that's possibly going to have, it's a good indication of something being an electrophile is having a positive charge. So we've got ethene over here. We've got ethene, and we've got HBr underneath the ethene. But hang on a second, HBr does have a charge, right? Because it's a polar molecule. You'll remember from F321 that, you know what, bromine is more electronegative, so it's going to have a delta negative. Hydrogen is less, so it's going to have a delta positive. Now, what happens, right, is the double bond, the CC double bond, is a region of high electron density. So CC double bond, high electron, high electron density. So because it's got high electron density, which is a result of the pi bond, in addition to the sigma bond, but it's to do with the pi bond, right? The electrophile, so because the H is slightly positive, it's got a slight positive charge, right? The electron pair from the pi bond, the CC double bond, is attracted to the slight positive charge on the hydrogen. And what this does, it causes the carbon-carbon double bond to break. So how do we show this in a situation using curly arrows? Well, let's show this. It's not hard at all. Okay, so what we do is we start with a curly arrow from the center of the middle double bond going towards the hydrogen. Okay, so you need to make sure that the curly arrow starts at the double bond. Okay, it can't be away from the double bond, it actually needs to touch the double bond. Okay, OCR and pretty much all examiners and all exam boards are strict in making sure that they actually originate from the correct position. So what happens is the pi bond, because it's got a high electron density, right, the electrons are attracted to the slightly positive hydrogen in the HBr because it's polar, right, which causes double bond to break. Now, a bond is formed between the carbon, one of the carbon atoms, because we've got two, one of the carbon atoms, and the hydrogen to which we've selected. And we show this simply as that. So we've now got that so far. Now, because we've formed a bond, we've broken up the CC double bond, we formed a bond with the C and the H, right? The H is no longer bonded to the bromine, right? The H is no longer bonded to the bromine. So the HBr bond breaks. And again, we're going to start off from the actual HBr bond, right? Making sure that it touches the bond. And we're going to move the arrowhead towards the bromine, right? Now, notice that on the first curly arrow, I've coloured in the arrowhead, and the second I haven't coloured it in. It makes no difference whether you colour it in or you don't. Just make sure that it's uniform, okay? So over here I've done a coloured and an uncoloured. Just make sure it's uniform. I'd just say leave it blank. Right, okay. So we've now broken the HBr bond, and you'll recognise that, you know what, a HBr bond is simply a covalent bond. We're moving the shared pair of electrons from the HBr bond to the bromine, or rather what is now a bromide. Right, and you'll notice that this is a heterolytic, oh my gosh, right, well, if my pen decides to work, which it doesn't, right, okay, it's simply a heterolytic, oops, I have no idea what just happened there, let's just draw that again, heterolytic fission, okay, so we're essentially left off with a bromide, right? Remember, it's negatively charged because of the nature of heterolytic fission, and it's also got a lone pair of electrons. Now, so far we've got this molecule here on the side. We've got this bit here. We've already got this attachment of the hydrogen from the HBr, which is what we wanted. What we are missing, however, is a bond on this carbon atom, and what I've done is I've added a charge, a positive charge on this carbon atom, because it's only got 3 bonds. It's going to acquire a formal positive charge, and this is known as a carbocation. This entire species on the right is known as a carbocation. Okay, so it's important that we can recognize this species on the right as being a carbocation, right? Now, what do you think is going to happen now? Well, we've got this bromine species, a bromide species with a lone pair of electrons, and we've got a positively charged carbon atom. What do you think is going to happen using curly arrows? Well, it's pretty simple. The lone pair on the bromide ion, right, is going to be attracted to the intermediate product, which is over here, to the carbocation. So we're going to have a curly arrow going through the lone pair, and you can see here I've not quite made it certain that it's coming from the lone pair, so we need to make sure it's actually coming from the lone pair. Okay, so it's coming from the lone pair and it's attacking the positively charged carbon in the carbocation intermediate, right? This entire reaction between the bromide and the carbocation happens because the carbocation is unstable, right? Is unstable. Therefore, it reacts to form, yes, you guessed it, it simply makes a bond. So we've got that hydrogen, and now we've got the addition of the bromine. Done. That is all there is to it when it comes to a mechanistic approach using curly arrows when showing the electrophilic addition of hydrogen halides. Why is it an electrophile? Well, we've got a slightly positive charge on the hydrogen, so it acts as an electrophile in the HBr. That is all there is to it. The product is a haloalkane, right? In this case, it's bromoethane, right? That is all there is to it. There's nothing else to it. We will expand this in a future video, but this is the gist of it. If you can recognize this as being a electrophilic addition, and you can follow through what actually happens, so you can see that we're breaking the double bond, we're then breaking the HBr bond by heterolytic fission, we're then reacting the carbocation with the bromide ion, with the lone pair, and we're forming a haloalkane. If you can follow that through a series of logical steps using curly arrows, right, it's dead useful, because what's going to happen in the first module, well, in AS, organic reactions, particularly mechanisms, you will get quite a few of them, and they're usually worth around about 4 marks. Often 4 marks. It can go higher, right? But it's really easy. So practice, practice, practice. Right, I hope that helped. I will have one more final video showing how the electrophilic addition of non-polar molecules, because what we've got here is a polar molecule. It's not hard. We will talk about that when the time comes. Okay, hope that helps, and see you next clip.